What is the equation for the work done under an isothermal process? That is going to be written as this. W is equal to nRT ln V2 over V1. Now you could also write it this way. W is equal to nRT ln P1 over P2. And the question is, how are these equations derived? Now, you need to know that if you are able to derive at least one of it, you could actually change it into the other by use of Boyle's law. Now, you need to know that these expressions could also be written this way. If I didn't want to write ln, which is actually the natural logarithm, we're going to write it this way. This is going to be 2.303 nRT, and now we're going to have log to the base 10, and yeah, we're going to have V2 over V1. If you don't want to use this, you could also use P1 over P2. Basically, from Boyle's law, V2 over V1 is the same thing as P1 over P2. So let's see how we can derive it. Now, the first thing we need to do, we need to go to work done, because we are actually talking about work done. So we need to use work. We know that work is equal to force multiplied by distance. I'm just going to write that as x. Now, this distance could also be called as a displacement, because basically the force should move the object in a direction. So that should be a change in position, which basically defines displacement. Now, what if I wanted to write the change in work done? How is that going to be written? So that is going to be written as dw, and here we're going to have f dx, because basically it is this that is changing. The force is not actually changing. So this is what we have. Now, we already know that pressure is equal to force divided by area. If I wanted to make the force the subject, that is going to be F equal to PA, right? Now, we need to do something. Let's see this. If I took P multiplied by A and plugged it back into this original equation, that is going to give me PA dx. So let's just do that quickly. That will be PA dx. So it is actually from here that we need to do the stuff that I was talking about. If you have a cylindrical column like this, and you actually wanted to find the volume of it, this is actually the area of the circular surface, and if you wanted to find the volume of this, you need to multiply it with the height. Now the height, I'm just going to write it as dh. dh is the same thing as dx. So the volume of a cylinder is the same thing as the area that is across, no, that should be the area for the circular surface, and that is actually multiplied by this. So if you actually wanted to find, if you actually changed the height of it, you're also going to change the volume. So as the volume changes, you actually have a change in the height or the distance in a vertical dimension of that object, right? So here we can see that the change in volume is the same thing as a dx. Now that is basically what we wanted. We wanted to make this to become this so that we can use it to plug back into our original equation rather. So dw now is p dv. Now next up, so first of all, we have this dw is equal to p dv, right? We just need to hold this one at the back. Now next thing we're going to do, we need to take ideal gas equation. We know that PV is equal to nRT over there. So if I wanted to make P the subject, that is going to be nRT divided by V. So what I'm going to do, I will just take this and plug it as P in the original equation. So for this equation, dW, that is going to become nRT over V multiplied by dV. That is basically what I have. Now, as you can see, we have dV, which means a change in the volume, but we don't have a temperature as a change. And that is actually reasonable because we're talking about an isothermal process, which doesn't actually have a temperature changing. That is the basic meaning of an isothermal process. Now, this is what I'm going to do. I want to integrate both sides so that I would actually remove these change or differential forms from both sides of the equation. So that makes me to bring out the antiderivative of each side. So that is going to be integral dw, and here we're going to have nRT. Now, as you can see, n, r, and t, they're actually constants. So I don't actually need to integrate them. I basically need to take them out. So this is going to be nRT, and I would have integral 1 over v dv right there. So on this side, we know that antiderivative of the change in w, that is basically going to give us the w. So I'm just going to write it here. Then we have over this side nRT. And here now we actually have ln v. So this is going to be ln v. And now this needs to be carried out at upper limits and the lower limits. So this is going to be a v2, and here we're going to have a v1. Now you need to know that this also has something like that. If I wanted to differentiate this in a definite form, this will be something like this. So maybe I just need to write it out there. You're going to have a w and a 0. So in this case, we have w to be the upper limit, and 0 is actually going to serve as the lower limit. Over here, we have v2 to serve as the upper limit, and v1, that is going to serve as the lower limit. So this basically is how you work definite integrals. So I just need to wipe out some stuff. Kind of clear these ones out. Yeah. So how can we work the stuff on the left hand side? Basically, this is how it works. You're going to take the first, which is the upper limit, and substitute it as the variable there. So in this case, that is w. W substituting w is basically still going to give us a w. And we have the lower limit. So the lower limit should substitute as the variable in the second case. So you need to subtract that answer from the upper limit. So this is basically what you have. Then on the other side, we have nRT, and this will be ln. Here v will be substituted for v2, right? So this is going to be ln v2 minus, I'm going to take ln v1. So I basically use the lower limit and substituted v for it. So w minus 0 should give us a w, and here we have an nRT. Now we have ln v2 minus ln v1. This should actually give you v2 over v1. That is a law in logarithm. If you have log of a minus log of b, this is actually going to change to log of a divided by b. Excuse me. Now, why is that? That actually happens because we have the basis for each log to be the same. So this is actually log to the base 10. This is also log to the base 10. And so that basically is the reason why. So as you can see, we have actually derived the equation for the work done under isothermal processes. But how can we actually change this stuff into having a P1 over P2? Now that should actually come off very easy, because you know that from Boyle's law, we have a P1 over P2 to be equal to V2 over V1, right? So instead of writing this in a case where you were not actually given any volume, you could actually use the pressures. So if I did that, I would have this new equation. This is nRT, ln, you got V2 over, whoa, I need to change this. So this should be P1 over P2. And so that basically is the way or the form that is needed in order to derive these equations. Now, if you will recall, I actually had another form of this work done, right? We actually had something like this. We had W is equal to 2.303 nRT, and then we had log to the base 10 and V2 over V1, right? So the question is, where did this come from? And how is it that we now have a logarithm to the base 10? Because ln means log to the base e. So how did that change come about? So let's see how to do it. Now, if you had W, let me use W is equal to nRT ln. I'm just going to use V2 over V1. That is basically the same thing as this one. So just going to clear this out. Clear these ones out. Now, there is actually a law in logarithm. If I had log to the, let's say log to the base a of b divided by log to the, let me change it and write it this other way. If you have log to the base a of b and I wanted to change this, I wanted to introduce another base, I would actually change this form into actually a fraction. So let's say I wanted to introduce the base c. That is going to be log to the c, log to the base c of b. And over here, we're going to have log to the base c of a. So what served as the initial base will become the subject for the denominator logarithm. And what was the subject for the initial logarithm? That will serve as a subject for the numerator logarithm. So if you understand this, we're going to use it in this case. Now, we already know what ln means. So for ln, we actually have log to the base e, and that is with a subject of v2 over v1. So this is the subject, and this is actually the base. So what we're going to do, we're actually going to introduce the base 10. So this is what we're going to have. This will be nRT, and here I'm going to have log to the base 10, and of course v2 over v1. And this will be divided by log to the base 10 of e. That is actually what you have. Now, if I wanted to take this away from the this form, this is what you're going to have. We're just going to have nRT multiplied by log to the base 10 of v2 over v1. And this would also be multiplied by 1 over log to the base 10 of e. That is actually what we have. Now it turns out to be that 1 over logarithm to the base 10 of e, that is actually a constant, and a numerical constant for that matter. So we actually know what it is. If you punched this into the calc, that would actually give you 2.303. So basically what we have is 2. Okay, let me write it in a more chronological form. So this is going to be an nRT, and here you're going to have log to the base 10 of v2 over v1, and that is multiplied by 2.303. So this is what you have. Now I could also well take this to the front, and so that is actually where we got the stuff that we got. So I'm just going to write it over here. So the work done is equal to 2.303 nRT logarithm to the base 10 of v2 over v1. So if you don't actually want to use this formula to find the work done, you could still well use this formula. That still works. Okay, so that will be it for this video.